Hello everyone. With this video, I'm going to start a new module called as the query processing and query optimization. Now, in any real world database system like Postgres or Oracle, so this is actually one of the central pieces of that system, and there's a lot of technology and ideas go into making the query engine very efficient, but all those details cannot be covered in an UG level course on database systems. So I'll give you an overview of what all kind of things go into query processing and query optimization, and hopefully that will give you a brief idea on how the industry thinks about these problems, right? And for more details, we have an advanced course on databases. There I cover more on query processing and optimization. Okay, let's start. Okay, so this is an bird's eye view of your uh, query engine, so to say, right? So first you have your SQL query, right? So you give the input as select star from somewhere, some tables, and then the SQL query goes through an parser or translator, whatever you want to call, and that parser, it will create an relational algebra expression for your query, right? And this relational algebra expression goes into the actual query optimizer module, and that optimizer will look up some statistics about the data, things like what are the table sizes, and if you give a where clause, how selective is your where clause, and so forth, right? So it will use those data statistics, and then it will come up with an execution plan, right? So in that execution plan you have things like you know for, let's say that you have an join operation in your query, right? So the evaluation plan for that query will give details on such that such as what algorithm should the database use for performing that join, right? Or if there is some kind of an where clause, let's say that you do something like select star from employee where salary less than 50,000, right? So this where clause, there can be more than one way of evaluating these where clauses, right? So the query optimizer goes through all these operators which are being used in your SQL query, and then comes up with an quote unquote optimal execution plan, right? And it uses different kinds of statistics about your data, whatever indexes you have, and then that annotated plan goes to the evaluation engine, which actually does the job of evaluating the query and returning the answers, right? So you may notice that when I say optimal, I say quote unquote optimal. The reason for that being that, remember, when you submit the query, you're sort of waiting for the answer, right? And there is a set amount of time which will go into evaluating whatever plan the optimizer comes up with, right? Because there is a bit of an execution time there also, right? So the database people, they always have this kind of a trade-off where the database engine tries to decide how much time does it want to spend in coming up with a good plan, right? Because there are two things. So one is coming up with the best possible plan, and then actually going ahead and evaluating it. Now if you spend too much time in just coming up with the most optimal way of evaluating this query, you have already lost the game, because the query response time goes up, and suddenly you are losing clients. Okay, so a database engine always has to trade off. Does it want to come up with the most efficient plan? How much time it may take? and after it comes up with that execution, the most optimal time, how much time actually is going to spend evaluating that query, right? So typically what the query optimizers do is that they have some set of heuristics, and they will quickly try to come up with an execution plan, right? So that not much time is spent, and then you just go ahead and evaluate, right? And in high end databases, really state of the art deployments, there there is some kind of even a feedback loop which goes on, right? So a database admin may see that this query is taking really long time to execute. Then he may actually ask the optimizer to come up with the most efficient evaluation plan also, right? So there is a feedback loop going on. So the thing to take away from this slide is that if your database is huge, like it's going into petabytes or terabytes at least, and let's say that an unoptimized query is taking hours, maybe half a day or so to evaluate, and it's very much possible, by the way. When you have data sizes which are going into terabytes, you can easily have a query with multiple joins and all that, which can easily go into hours for execution, right? So at that stage, usually the database administrator, they try to, intervene and then, see what is the most optimal way, or even they may even, sort of push the optimizer to come up with the most optimal plan, right? So then, the optimizer takes his time to come up with the most efficient way of handling that query, and then stores it, right? So these kind of things are usually done in what is called as data warehouses, where the same query is executed again and again on the new data sets as the data set sizes increase and so on, right? So whenever we have a situation like that, when the same query is being executed again and again, we also like to call them as canned queries or planned queries, right? So there is bit of an incentive for the database to actually spend some time once to come up with the best possible execution strategy for the query and store it, so that when the same query is fired again and again by different people, the query optimizer does not have to spend time optimizing the execution again and again. It will just go ahead and look up whatever it has done before, and then go ahead and solve that, right? So this kind of things work best when you have a set of queries which are executed again and again on the database, right? So typically data warehousing is a class of database systems where these kind of things are done, right? So in a data warehouse, basically, uh, it's a classical example of data warehouse could be uh, analyzing transaction records from, let's say, Reliance Geomart, right? So it collects all the transaction data, which it is getting from the stores, and then they put it into large data warehouse to see what kind of trends are showing up, right? So in those cases, you have more or less the same query which is executed again and again, maybe once every few days, to get the current analytics on what is selling of good, what is selling of not so good, and so on, right? So in those cases, the DBA or even the Oracle, the engine itself will try to come up with an optimized plan. Okay, so hopefully you you got an idea of how things are done in the real world. Okay, so now let's move forward. So here in the next few slides, I have just a simple example to show you how query optimization is done. So let's say you have an query something like this: select salary from instructor where salary less than 75,000, right? So if you were to write an relational algebra expression, you can write something like this, right? So instructor, you perform the select operation on that, and you perform the projection operation on that, and then followed by the select operation, right? But from your relational algebra, you know that this is equivalent to this, right? So for the same query, you have multiple equivalent relational algebra expressions, right? And for any one given relational algebra expression, uh, for all these operators, this project operator and this select operator, you may have several candidate algorithms, right? So of course, for this projection, you may not have so many options, but when you have something like a join operation, then your suddenly your choice of algorithms increase much more, right? So now if a query optimizer has to come up with the most optimal way, just imagine the search space that it has to go through. So for one thing is that your SQL query has multiple equivalent relational algebra expressions, and within each of those relational algebra expressions, you have for each operator you have multiple algorithms, right? So the search space is actually twofold. First is the along the dimension of the possible relational algebra expressions itself, and then the second one being that for any one given relational algebra expression, then you go inside, and for each operator you have multiple algorithms, right? So this is just to show you that the query optimization is not an easy task, and probably which is why this is still an active area of research, especially when you go towards distributed databases and all that, right? But just keep it in mind that query optimization is not a trivial task, right? Okay. Yeah, I think this I already covered. What is an evaluation plan? Okay, so now when you are measuring the cost of a particular plan, let's say that you fixed on one relational algebra expression, uh, and then let's say that you fixed some algorithms for each of the operator. Now how do you measure the total cost of using this plan, right? So again, you have multiple metrics. The total cost, if I were to think in terms of total elapsed time in answering the query, you have multiple factors which contribute to this, right? So you have disk accesses, you have the actual CPU time also which comes into picture, and then there may be things like network communication, uh, but these factors which have the potential to contribute to the total execution time, we may not be even able to make an estimate on all of these, right? Sometimes these things are even too complicated to estimate, and it depends on so many things that a priori the query engine cannot do it. And if it tries to do it, it will probably spend so much time that the whole point of having a query optimizer itself is lost, because you have spent now too much time in just optimizing the query, right? So the what we do is that we do some simplifying assumptions over here. So what we do is that we try to estimate, at least for simple standard relational database systems, which you have been using for so long. uh, there in the query optimizer, we will try to estimate the total uh, cost of using a particular plan in the terms of number of blocks accessed. So these blocks could be either for writing or for reading, right? Because you may remember that disk access time is usually much higher than your CPU time and all that, right? So when we are evaluating alternate query plans, we'll try to evaluate them from the perspective of how many blocks am I going to access, right? So there is also a factor of the number of seek operations, which you remember that seek operations are usually the maximum time taking, but in fact I'm going to even ignore the seek operation. Why? Because for us to get a good estimate on the number of seek operations, you also have to know how your file is divided in your disk. Is it monolithic? No, is your entire file stored in one contiguous block of memory, or is it broken down like a linked list and all that, right? Again, these things are hard to estimate. So for that reason, the query optimizer even sometimes even ignores this cost of seek operations that are going to be involved in your query plan, and it just works with the total number of blocks accessed, either for reading or writing. Okay, so now we are going to go through some query processing algorithms. Okay, yeah. Okay, so the first one being for the select operation, right? So you have a query like this, select star from employee where salary is less than 50,000, right? Now, in order to evaluate this where clause, you have to go through the file. If there is some index, we'll see how to use that index. But if there is no index, then you may have to go through the entire file, right? So this is the very similar to what it as linear searching. So in linear searching, what we do is you scan through the entire file block by block and test all the records to see whether they satisfy your selection condition or not, right? If they satisfy, then you collect all those tuples you know uh, and then return them at the end after doing some projection, right? So now if you were to estimate this, the total cost of doing this operation, then what would be, right? So there are bit of an assumptions over here. So in the literature, we say that if the select operation is on a key attribute, that means you are searching for select star from employee where employee ID is 2000, right? So if you have a query like this and then you perform a linear scan, the assumption is that on an average have you will have to read half the number of blocks in the file. So BR is the number of blocks in the employee file, and if you are searching for a key searching for a particular tuple and you are searching on the basis of the key attribute, right, you may have to do half of the you may have to read half of the file, right? So that is the BR by 2 block transfers, and then this the number of seek operation. As I said before, we cannot estimate this until unless we know that how your file is actually stored in the hard drive, right? If we make an assumption that all the blocks of the file are stored in contiguous memory locations, then there will be just one seek operation, and then remaining ones will be only block transfer time and maybe little bit for rotational latency and all that, right? So you remember these expressions. Okay. uh, okay, and then in the absolute worst case, as you can guess, in the absolute worst case, you may have to read the entire file, right? So for example, you are not performing a selection on the key attribute. You simply have to go through the entire file to take out all the tuples which pass a certain um, selection condition. In that case, you can assume that you will pretty much read the entire file, right? So for example, a query like this: select star from employee where salary is less than 50,000. So for that query, if you're doing linear scan, you can safely make this assumption that you are going to read the entire file, because your file is unordered. The records with salary less than 50,000 can be all over the place, right? But if your selection is on a key attribute and you can stop for finding the you can stop as soon as you find your desired record. Then you can assume that you will read approximately half the file, right? So this is just an estimate. Okay, let's go forward. Yeah. Now, so that was the cost of linear scan. Now, if you have an index on your file, and then, let's say that you want to use that index, right? So how much will be the cost of using the index for performing the select operation, right? So let's say that you have an primary index and your condition is equality on the key attribute, right? So what this means is that you have a file, let's say employee file, and the file is, let's say, ordered on the employee ID, and your query is select star from employee where employee ID is equal to 2000, right? So it's the equality condition on a key attribute, right? And then let's say that you have a primary index. So under all these conditions, you just have to search for one particular record in the file, right? So the total blocks accessed would be the height of that primary index, and then plus one additional read operation to actually go ahead and retrieve the full tuple, right? So remember that in an index, from root to the leaf, you will be accessing height number of blocks. You as you may remember that whether it's primary index or for that matter even if it is b plus tree index, each node is one disk block. So if you have to access height number of nodes, you will access height number of disk blocks. So that part is this height. And then once you reach the last level, the leaf level, you get the record address, and then you actually have to go ahead and fetch that record from the file. So that is one additional disk IO. So therefore, when you put everything together, uh, I'll say that when you have primary index and you're searching for equality condition on a key, you're going to access height plus one number of disk blocks. Okay, let's see next. Yeah. Now let's say that you have a primary index, but you are searching for uh, some records such that they all match based on equality condition, right? So let's take an example here. So let's say that again we'll go back to our employee file, and let's say that given that this is a primary index, and the file has to be sorted obviously, and let's say that I constructed a primary index on the employee table, and the attribute on which my primary index is constructed is the department number, right? So in other words, your entire employee file is sorted on the department number attribute, right? So and now you give a query like retrieve all the tuples corresponding to the computer science department, right? So file is sorted on the department name, and you have constructed an primary index on top of it, right? And now how will your searching go? So let me take an example of a primary index, maybe that's better. Okay, so here is an example of a primary index constructed on an non-key attribute of the file. By the way, when a primary index is constructed on a non-key attribute, it's called as clustering index, right? So here, you have the data file and you have sorted it on the department number, right? So now in your index, what will happen is it will take the unique values and it will store the first block where it appears, right? So let's say department number one appears for the first time in this particular block. So I will store a pointer to this block in this here, right? So department number two appears for the first time in the same block, and then maybe several in the next one also. But when you are storing the index for department number 2, you will still store the first block where department number 2 appears, right? So now if you have to do select star from this employee file where department number equal to 2, you will come here, check out department number 2, go to this block, and retrieve the tuple corresponding to department number 2, and then there is always a link to the next block of the file. This is always a link. So from here you will jump here and then retrieve this record also, and so forth. Whenever whatever further records are there, you will keep on retrieving them, right? So same is the case here also. Let's say you take department number 3. Department number 3 appears in both these places, both these blocks, but you will store the address only of the first block where department number 3 appears, right? Because now if you have to, as similar to the case before, if you have to retrieve all the records for department number 3, you will first go here, retrieve all these 3 tuples, and then follow the next pointer to go to the next block, and then keep retrieving all the tuples where department number equal to 3, right? So this is how a primary index on non-key attribute works like, right? In over here, each value appears only once, right? So here I do not repeat 1 3 times, right? And now if I have several of these, I can construct a multi-level index on top of this, no problem. That's just constructing primary index on self again and again until unless you have just one block left, right? So now in a case like this, I am saying that select star from employee table where department number equal to 3. So first I have to search the tree from root till leaf to get this uh, block address of the first tuple that appears for department number 3, right? So I have to access height number of blocks for that. So that height is this number, right? So from root to the leaf, I have to access height number of blocks, and then I'm assuming that this department number 3 appears in B blocks in this file, right? So I have to access height number of blocks and then go to the first block where 3 appears, because I'm, let's say, in this example looking for department number 3. So let's say that this department number 3 appears in maybe 4 different blocks contiguously, right? So I have to retrieve 4 blocks, basically all the tuples for department number 3, right? So that is how you derive costs for an query processing algorithm, right? So this height is for the height of the tree, and then B is the number of blocks containing the matching records. And given that this is a primary index, your file is completely sorted, so all the all the tuples corresponding to a department will cluster together, right? So all the computer science records will cluster together. Now if the computer science records are spanning across 10 different disk blocks, so this will be just 10, right? So the reason I'm going slowly over these expressions is that you can very much expect in your exam that I will give you a query processing algorithm, something like this. I'll say that this is the index and this is how your algorithm is processing to solve a query. I can ask you to come up with these expressions, right? It's I have done it in past, right? And you should keep it in mind, right? So don't try to mug up these expressions. Try to understand how these are actually derived from a given algorithm, right? So let's take one more example here. Now let's say that you have an secondary index, right? And the secondary index, it's a B plus tree index, and your search operation is equality on the key attribute which is being indexed, right? So let's say that you have the employee file again, and you have constructed a B plus tree on the employee ID, right? Your file is not sorted, but there is a B plus tree which is being constructed on the employee ID attribute, right? Now you are going to use this particular tree to solve your select operation. So let's say your query is select star from the employee where employee ID is 2000, right? And you know that employee ID is the candidate key, right? And you have a B plus tree on it. Now, how many disk blocks will you access for solving this query, right? So you're going to access height number of disk blocks plus one extra disk access to actually go and fetch the record, right? So let's take a simple example of a B plus tree to understand this. Okay, so let's assume that this was your B plus tree, and these were the employee IDs. And now if you have to retrieve the and all the details of the employee ID, let's say 17, right? So you're going to search for 17 from root till leaf, right? So this will require height number of block accesses, because each node, as I said before, is one disk block. So first you're going to access the root, and then you follow this pointer, then you access this particular disk block, and then finally you access this particular block in the leaf, right? So you retrieve this entry, and then you have the tuple address where this tuple corresponding to employee ID is stored, right? So the total number of accesses is 111, so 3 plus one extra to actually go to the file and pick up that, right? So therefore, the total number of block accessed in case of a B plus tree, and let's say you are searching on an attribute which is the candidate key, then the total number of blocks accessed will be height plus 1. So height for the tree and 1 is to actually go ahead and fetch that record, right? So now let's say that if your uh, this index which has been constructed happens to be and the attribute happens to be an non-key attributes. That means there can be duplicates, right? So again we can take the example of the department number. Let's say that these are the department numbers which appear in your employee table. So obviously each department number can appear multiple times, and then you constructed a B plus tree on this department number attribute of your employee file, right? And then you search for, let's say that your query is select star from employee where department number is equal to 8. So first you have to search for this department number equal to 8, so that will be height number of disk blocks. And then if you remember closely from your previous lectures, I said that whenever I'm constructing a B plus tree on a non-key attribute, over here I do not store the addresses of the tuples. I store the address of a disk block, and in that disk block I store all the tuples where my uh, department number 8 appears, right? Department number 8 can appear all over the file, because your file is not sorted, right? So you can make some assumptions that if each department has maybe just maybe 10 at max 20 records, and under such assumptions you can come up with an expression for this. I think I have an example in the later part. Let me just jump ahead and get that here. Okay, here it is. Uh, yeah, so as I said before, we are using a B plus tree to search for records, and the attribute on which B plus tree is constructed is an non-key attribute. Okay, and I think we were taking the example of the department number, right? So we assume that this is the department number, and we are looking for department number 8. So first thing is that I'm going to search to find this particular entry, department number 8. So for this, height number of blocks will be consumed, right? And then given that this is a non-unique attribute in B plus tree, I said that the pointer from this guy at leaf level is not going to store the all the record addresses where department number 8 appears. Rather, it stores a pointer to a disk block which contains the record addresses. Okay, and that can be just one block or multiple blocks, right? But this is just going to store an address to a memory location, which actually stores the list of all the tuples where department number 8 appears, right? So in that kind of a setting, what will be the total cost? Okay, so the total cost can be approximated something like this. So height, from where the height is coming, and then this portion of the expression, what I'm calculating here is the number of blocks that will be required to store the record addresses of department number 8, right? So SB over here is the expected number of records matched. So that means, if you're looking for department number 8, how many records do you expect from department number 8? If you don't know the precise number, you can even roughly approximate or have an upper bound and all that, right? So if SB is the expected number of records that I'm going to get from department number 8, so I have to store from the leaf level, I have a pointer, and then I have to store SB number of record addresses, right? So this expression is basically telling me the total number of disk blocks which are required to store SB number of record addresses, right? So that is why I'm saying that it is SB divided by blocking factor of that. How that means, in one block how many record addresses you can store, and then finally the seal, right? So this is the number of blocks that will be required to store SB number of record addresses, right? So from here you will get all the, you do the height number of block access, and then you do these many number of block accesses to get all the addresses of your SB records which you are expecting to match, right? And then for each of those SB records, you actually have to go ahead and fetch the details from the file. So this SB is that part, right? So again, three things. So first is accessing this B plus tree, and second, accessing the extra blocks to store the addresses of the records, and then actually going ahead and fetching the all the tuple details from those record addresses, right? So therefore, if you are using a B plus tree on a non-key attribute for searching, this is the total number of blocks accessed. This is the expression of that. Okay. Okay. Now the last part, that here, your search condition was always equality. Select star from employee where employee ID equal to this. If it was a key attribute or a non-key attribute, based on that, your expressions were changing, right? Now if you have a range query, something like this, select star from employee where salary is between 100 and 200, and then you have a B plus tree on the salary attribute also, right? Then you can use the B plus tree to get those tuples, right? Now how will you use that? Let me again go back to this, right? So now, so first let's take a simple example where this B plus tree is on a key attribute. That means we are using employee table, let's say employee ID, right? And my query is select star from the employee table where employee ID is between 100 and 200. So first you are going to look for the employee ID 100, or let's say in this take example, let's say that I want employee IDs between 8 and 24. So I will look up the employee ID 8 in my B plus tree, and then I am going to do a leaf scan. Remember that leaves are always interlinked, right? So and in the B plus tree, the leaves are always interlinked. So I'll search for 8, and then I will just simply do a leaf scan and retrieve all of the record addresses from these entries until unless I hit 24, right? So this was the way in which we are going to do an range query on B plus tree, right? If your attribute on which your B plus tree you are constructing, if that was an non-key attribute, then you know that there are extra blocks stored here which will have the addresses. Nevertheless, the algorithm remains the same, Whenever you are doing a range query using B plus tree, and your range is between, let's say, between, let's say, x and y, so you search for x in the tree, and then you do a leaf scan until you reach the y, and then in the middle, whatever the entries are there, you fetch all the data corresponding to those entries, right? So this is how a range query is solved using B plus tree, right? uh, Okay. So I will not go into the expressions, cost expressions for range query. They will be much more complicated. Uh, okay. So maybe for an higher course, we'll cover that. For now, uh, I'll be happy if you understand the cost expressions for, these, the ones which are given in the slides. If you are able to fully understand them and not try to mug them up, I'll still be happy, right? So don't worry about cost expressions for range queries. If I have time, I'll cover them. Otherwise, maybe not. Maybe it's in senior level course, right? Okay.